continuing with the practical aspects of using HPC, we have the next presentation where we have the projects.
The topic that we've been asked to discuss now is computing proposals. Now, this topic is actually not relevant right now in India because we don't have a well-structured high-performance computing facility where regularly you submit proposals and you get right. What the current landscape in India is, several institutions or universities have their own systems. You access them either being a member of them or through collaborations. The HPC facilities are actually quite small. There are total number of cores going from 1,000, like typical 2,000, 4,000 cores, depending on some of the institutions that you have. Universities are not currently well served by HPC facilities. National Supercomputing Mission has come up. It is still in its very nascent phase. It has deployed some facilities all across the country. But again, the way to access them, it's not very clear and also not very open because it's in a very nascent phase. The coordinators are still figuring out how to build these things. In India, we've started this. NSM has started, I think, 3 or 4 years back, whereas in abroad, they have been regularly doing this business of setting up clusters, setting up HPC facilities for a very long time. CDAC in India was there for a very long time. CDAC does serve general researchers. You have to apply for time, but they have their own mechanisms. So what I'm going to discuss today, I don't have a structured talk for this. So what I'm going to just share with you is some of the experiences that we had. And there is no set formula for writing a computing proposal. But again, like Andrea discussed yesterday, I will just briefly describe some of the best practices. And when a system administrator looks at your proposal, what is that? What are the basic points that the person did? Okay, so that is the main thing. So I will show you some of the proposals that we did over the last few years. Again, this was all before I came back to India. So right now, the way it works is we have international collaborations. We approach the international collaborations and get time from international cities. So I still, I'm running things, but it's a PI from an Indian facility. You are not always eligible, except for certain systems, for grace. And as an international person, certainly can apply for Taiwan, Japanese, so can do that. Right. The first warning when you're writing a proposal is remember that your proposal will be required general audience. You would approach it from the point of view of astronomy and astrophysics because this is the audience that is there. But the major fraction of the usage is done by people from the engineering disciplines, people from biology and genetics. So the committee that will review your proposal will have a mixed committee. If you just load and cram your proposal with lots of astrophysical jargon and text, Ken Schmidt law doing this and that, nobody will understand the proposal. So you have to have a balance and have a clear, concise description. Not to go into too much of detail, of course, if you just write in completely general term, the fact that you have some expertise will be lost and you would lose it. So the novelty of the science has to have a balance between the depth of the rigor as well as the meaning of the general sense where it means but not necessary for your discipline. Yes. So the proposals usually are submitted so this kind of proposal I will discuss in more detail shortly. I'll give you 2 examples where I currently use 2 facilities. So there are open calls from the facilities. Now, it may not be that the facilities themselves are coordinating these calls. So for example, I have access to the Australian supercomputing infrastructure and the Italian supercomputing infrastructure. The way to access them are through different means. One is there is something called the National Supercomputing Allocation Scheme in the Australian environment. It's called the NCMAS. That is done under the board that does it has representations from the people of the system administrator. But it is done by people of a consortium of different HPC systems. And then you submit the proposal. They have an expert committee and a technical committee. So the expert committee will have like scientists judging your case. The technical committee will then have a review with the technical aspects of the code. It's not that the technical committee will not comment on the science, or the science committee will not comment on the technical. You have there are other avenues to do that. For example, certain disciplines like astronomy and astrophysics in particular also have some MOUs with certain of the systems to get a dedicated allocation in the system. Again, for Indian context, all of these are hypotheticals. We don't have any such dedicated transparent architecture in this moment. But it does not mean that it will not come up in future. So with the NSM and helping the computing infrastructure to grow, we are hopeful that this will come up. But as a community, we should prepare in advance that when a proposal call comes, ahead and writing the 10th draft, and then the final draft version 1, version 2, like that. You should have a draft ready with you that if proposal comes, you submit. So again, the astronomy community has it. So you can submit through those allocation schemes. For example, one of the allocation calls that I've given here, this is specifically for the university where the system is located. It's ANUMAS. There's another called ASTAC, where say some 20 million CPU hours is given to that. 20 million is actually quite small. But if you go through different allocation schemes, you get small allocation, and you can serve your project in this way. All right. So the first thing, as I said, keep it a fair bit of balance between the details that you want to visit for the computing. Third, the second important point is, so the science is fine, but more importantly, you have to show that you have some technical expertise to handle this course. If you just say, I have run Pluto, I know how to run it from the user guide, and I want to use 2000 cores for 2 months, it will be difficult to justify for a person giving the time to trust you that you will actually use the time judiciously. Again, what I'm going to say is a rough number, and I recall this from a past proposal somewhere. The time to dollar ratio was one CPU a minute was almost like $1. Okay, so the research that you do it will be different from the Indian context because you convert into rupees. Also, our electricity rates are cheaper. So, but the research that you do, single CPU run that you do, for the mind, you should remember that you're running using things the orders of millions of dollars. Similar amount is also done for observational astronomy. A single observing run, we as users are away from this, but from the system administration point of view, a lot of money is spent on maintaining the structures, the electricity bills. If for an observatory, they're rotating the dome, the staff present there. So a lot of money is spent on the computing side. The most important is the electricity bill. So a lot of money is spent on cooling the systems and then upgrading the system. So the research that we are doing is expensive. Why am I saying about the money? Usually in research, we stay away from the monetary side of things unless we have to get some proposal. But you should appreciate the fact that what you are doing right now, unless you do a dot slash somewhere and you get some nice plus, it's expensive research. So the time that you get, you on your own should be judicious in using it properly. It's not that for every run that you make, you have to pay per hour. That is not how it works. From my own personal experience, I'll show you the proposals that I've given. I have said I'll run 4 models and do this and that. 90% of those time is spent on testing the code. Only 10% of it is what I have done for production runs. Because from practical experience, again, you can always think, okay, I'm ready with my setup. You run something, and as Andrea said, it's not just pretty pictures that drives your science. You have to test and verify it. Something somewhere inevitably goes wrong. And the fact that you would make mistakes, you would not think of everything in advance before running the code. It's something that you should internalize. You cannot, be perfect at the get-go. Of course, after you run those models, in the next iteration, when you continue the project with a new proposal, you'll be more perfect. You will not be wasting so much. Okay? So, in this context, again, what is important to understand is do not ask for a huge amount of time at the first go. When you are an early period researcher, you may be over exuberant. You may think that I'm capable of running these models. I know what is happening. I use to the maximum capacity. But you should always take things in steps. Some of the clusters and scalability facilities have this nice architecture where they have clear level of access. So the usual advice that is given is when you start a new project, always ask for a small location with the experimental setup. For example, let me see the Jamaica application. Okay, I don't have it right now, but for example, this is the Marconi allocation that I'm using. Okay, I'll go to the system machines there differently. So for the Italian systems that I have been using for the last 5 years or so, there are three types of allocations: Type C, Type B, Type A. Type C is given every month. Every 15th, you can submit of a very short amount, 100,000 CPU hours. 100,000 CPU hours might seem substantial for a few, but it's actually not if you are used to running very large scale models. How do we use it? We use it either to test the scaling, the performance. I will show you the scaling, performance of our code. If you are using this machine for the first time, you have to demonstrate that your code is able to perform on a large scale distributed platform. And using those plots, then you can apply for the large scale groups. Also, suppose you are not sure that one secret mechanism that you have devised is actually working. The typical way we develop codes or during the developmental phases, we devise a simulation of the order of 50 by 50 by 50 cells. You run things. First thing is to check whether you get any segment faults. You will inevitably get something. You've forgotten some variables somewhere. You've not closed some areas somewhere. You've over allocated areas. It happens. Once you're out of the set fault loops, then you test something and you will find that you've forgotten to include some viscosity term somewhere. All of these happens because it's a large code. And if you are heavily modifying, just using the skeletal architecture and just slightly modifying it, that's fine. But when you actually go to real world problems, and you have to do something more than what has been done, you have to heavily modify it. So again, a fair bit of warning. Although I'm very happy to see the level of independence people have received from this workshop, but it can also be a bit deceptive. So I will, as Andrea said, keep coding. But all the people say, revise your own problems. If you have a background in fluid dynamics, revise any the standard textbook problems. Make on a simulation. Every day morning, read the newspaper, run a simulation, let it go for 2 hours, and then check the results. In this way, you get the experience of running things, setting up new things, and modifying the internal architecture of the code. That is more important. Just say init.c, tutor.init, definitions.h1. You have to go inside SRC, inside MHD, and then modify macros.c to get something out. So this is the level that you should expect. Okay. So once you have some confidence that whatever subgrid or new thing that you want to propose works, then you go for a higher level of allocation. For example, I'll show you one of the class C proposals that I have. This is class C. This is class B. This is a class C proposal. Again, we did this because we were trying to set up a novel new technique, and we were not sure how the performance would go. You can see the proposal is very short. You have to just clearly mention. So in the first part of C, these are different proposing portals are different ways of splitting it. Either you can select a PDF document, or it has a Word form of layout. It's important to make sure that you have some sort of a formatting, because you must remember when the system admins receive this proposal, they'll get several tens, 50 proposals or so. If your proposal just looks like a collection of text, people will not read through. It's practical experience. As a reviewer, I face this as well. If your proposal is not well formatted, not well written, not easy to look at, if we have a deadline coming up tomorrow evening, and I have other works which I started reading the proposals from the morning. We'll just go through the ones that formatting. It's not that I will not read through, but I will give more attention to those that are easier to read. So format the proposals properly. You see, this is a very short proposal. With a very clear argument, I need this much of CPU hours this way. Why? And I want to test the code. That's it. Now, once we have done this, this is a more formal proposal.
What does these classes?
So as I said, there are 3 different levels of allocation. So the class C gives you just 100,000 CPU hours just to test your code. You can test the new physics. Class B, at least in the Italian systems, I think now the counting has changed a bit, but that time it used to be, I think, 5 billion. This is, I'm talking about 2018 to 2019 when we applied this. And the class A was much higher. So class B is a bit more repetitive to get through. So this is how I had written the class B proposal. So first, a brief summary of the research interests of mine and a list of publications. These are fine, but this is where the proposal starts. Important to note that if there is a space, give an executive summary. The proposal can be long, but if you give a short summary summarizing the contents of the proposal in the beginning, it makes it easier for the reviewer to just have a quick understanding of what is it that we're proposing. After that, people will go to the depths of and verify whatever you've written is clear of that. Again, as you can see, there was attempt to at least make points and create some formatting. So the things that we usually check for is A, scientific motivation. Clear objectives of the project. Now, the objective should be more defined and tangible. I will produce this plot, I will achieve this level of accuracy or something like that. It should not be very general that I will solve the solar chemistry. You have to be more clear and specific, and that is how people can judge whether you are actually serious or not. The project outline is very important. You should show that you have a well-defined plan in mind. If the time is given to you, what is the pace at which you will use this time? So I will come to the project outline later on, but here you should, I've given a summary of how I'm going to use this time. Let's get into it. Then the scientific impact. So what is the novelty of the results? Is it just repetition of what somebody has done? Is it I'm going to produce something new? Is it just incremental change? These are actually valid scientific queries. If somebody Group A has done it, and nobody else in the world has done it, you can propose that I want to run this code in my infrastructure to reproduce results and verify certain schemes. That is okay. Or you can have that have done some work in the previous cycle. Based on that experience, which has been successful on some papers or something, I want to extend it. That is actually highly rated because that shows you have the capability of running things and you can make definitive progress. It's not an open source. Okay, so now there's a description of research. There's nothing to say. It depends on what kind of things you do. Figures, if you can, are important. Why? So this is a visualization of a jet, the tracer of the jet going through and then coming back in a backflow. For one options. Why are figures important? Because as I said, people from diverse backgrounds will find the text a bit dense to go through. But if you have some figures, so again, nice people, people who are reviewing your proposal, they're experts. Do not try to fool them. Nice figures does not mean nice scientific results. But if you back up your results with some figure, that is helpful. Then the primary objectives, and more importantly now, It's a code description. So in the code description, at least for us, what we have to write is the Pluto architecture. Whatever code you use, you have to be clear and concise about what is the nature of the code, whether it it's kind of volume method or something else. What kind of architecture is it built on? Is it MPI, GPUs, things like that, or OpenMP, for example? And then what is the legacy of the code? Has the code been used elsewhere? Is it a new code? Where has it been tested? Things like that. Okay. And these are the, okay, I'll come to the, okay. Then I have given model setup and initial conditions. So in the previous sessions, I already had a scientific session. There, we did not give the details of how we are going to set up the model. So that is more general science. But here, code perspective, you should give some of the parameters that you give. So you want to vary, do a parameter scan. First thing, I want to launch a jet, but I want to change the Lorentz factor of the jet and see what goes to the ramp pressure, how it evolves, etc. So here you should give some quantitative details. So here in general, so what people will look at is, are you a superficial or shallow user who knows the hard analytical solutions, do not have a clear, concise idea or plan of how you are going to approach the story? That is something that you should clarify to viewers. I've given some critical diagnostics that I would do to bring out the results that I have asked in the scientific plan. And then it is the detailed work plan and the Gantt chart, which I will come to. Detailed work plan is you should give a list of simulations that you do. Now, as I said, so I have prepared a list here. 90% of the time, I try to do simulation 1 or 2. Then I found that HLC is not working. It's not up to the standards that I need. I need to use a different HLL. I went to a different HLL. It was more diffusive. So I had to go back to HLC, but then it again crashed. So then I did something like where the regions of instability is where I lowered the resolver to HLL. Like shock flattening was discussed to you. There is an option in Pluto. Here are lots of different fixes. Sometimes some weird cell gets your code stuck. So you have to find and devise a method of how you have to bypass that and at least make the simulation go forward a bit. Sometimes once you do that, things stabilize. So all of this you have to take into account that this will happen for you, and you will spend time on that. It's not wasting CPU hours. It is part of research. But at least when you're presenting to the committee what you're going to do, you have to give a detailed work plan. You want to run AEC simulations, and then justify what you think simulation A would require 1 million CPU hours. You cannot just bring it from the top of your head. You have to demonstrate that. To demonstrate that, what is important is to use a small scale navigation. Whether you can use your, whether you can use your institutional small scale cluster, run it on 100 cores, on a very, as I said, 50 by 50, 100 cube box. See how it goes. Find the total time required at scale. Then someone tell me, suppose I have a 3D simulation. It takes some total time T. I want to double its resolution, so increase the number of bits by 2. How much would the compute cost increase? How much? For 4? Why 4? Why not just 8? So I'm increasing the dimensions 2 by 2 by 2. So if I had 100 by 100 by 100, I'm now going to 200 by 200 by 2. Why is it? Somebody said 4.
Twice for every spatial cortex and one temporal cortex.
One temporal cortex, yes, from the CFM criteria. So your compute cost is increases by 16 times, not 8 times. So in this way, you can approximately scale up. But you should also remember that simply scaling up the problems in an MPI domain does not mean it will actually scale up by that. Because a lot of time is spent in internal communication. So you have to show the scaling of the code If the scaling of the code is linear, then the 16 time points. So typically what we do is when you start a completely brand new project, this is what we do. We run a small scale simulation. We specify the results of those in this proposal. Then we extrapolate how much time it will require. Now, oftentimes we cannot extrapolate accurately. For example, I have done a hydro simulation. I want to run an MHD simulation. How would I do the timings? You know the number of MHD equations that we'll be using. You know approximately the extra number of differential equations will be solving. Multiply it by a factor of few, depending on the extra equations that you solve. Rough guess. But best way is to test this on a small scale system and then again expand to the larger scale system. So this is how we sort of propose that we will do this in this simulation. Based on my experience of running this simulation either in the same cluster on the same scale. So that gives the reviewers confidence, okay, if this person knows what is the expected time, they have well demonstrated the expected time. And so let us give them the time to do that. Thanks. An important thing that I usually put in whatever school is not like this. It's called the damage group. So this clearly shows your attempted or planned usage for the different kinds of simulation. So in cluster practice, usually your accounting takes place every quarter, every 3 months. So your allocation is usually given in terms of 3 months. So if you get say 9 million CPU hours or 1 million CPU hours for the entire year, divided into 4, 3, 3, 3, something like that. So then, if you are presenting a visual representation like this, it inevitably helps. This is the feedback that we have received from the committee. Not everyone who have proposed it has given it like this. But whenever we have submitted, our group has been quite successful in getting it like this. The feedback has been very positive. So it's important to be clear to the committee that how you're going to show. Don't ambitious. Keep buffer frames. Usually when we propose, we always say the first month or so, we're not going to use the code. We're going to develop the code, we're going to test the code, and then we're going to use the code. Because then the expectation from the committee side would be to check at the end of the code, because when they allot the time to you in the next cycle, they will check your usage pattern. Not just the total fraction of time that you have used, but the average time that you have used. You have to maintain a steady average. It also should not be that just at the end of the quarter, you have a spike in computing usage. Even for a cluster that is not as well maintained like this, like a supercomputing discipline like this, even if it's your own institutional cluster, let's say, do not treat it as your own, desktop. Have some, conscience about it, that your institution is paying a lot of money to maintain it. Use it steadily. Do not run a code and then forget about it for 2 weeks and then come back and see the results. These are the things that people have done. And the only reason why we have become accustomed to it is because we don't have to pay anything from our pockets. There is no penalty for mal-usage of the cluster in the Indian environment. And this is what I'm telling you from a very young age, so that when you grow up and you tell your juniors or your students later, you can pass on this experience. In any of these systems, if we do not use it properly, our time is lost. For example, this is happened to us. We could not use the time for the first quarter, whatever. I was moving away, I was moving jobs. Other members of our group could not use time. We were granted, I think, 6 million. We used 4 million. In the next cycle, we are only given 4. So it is strict. If you do not use that full time, even if you have a good space case, you demonstrate it for the rest of the quarter we have used. The committee will feel that since you have been given something, you have not used it, your limit is 4 million hours. So you get. If you use it for the next cycle, you use it better. This kind of accountability is not there in small scale institutional concern that I will close it to you. So we are more understanding of the use of these things. Okay, so this is something, and then I wanted to show you something called scaling. So this is something that you should demonstrate. Even if you open Pluto, the user guide, you will find there is speed up. So what is speed up? There are 2 kinds of way you can show how your code performs on a distributed architecture. So That is called strong scaling or weak scaling. What does it do? You take a problem. It takes, say, 90 to run it on a single core. Now you run it on 2 cores, 4 cores, 8 cores. Keep on increasing the number of cores. And you, of course, that time will go down. Beyond a certain point, it will actually hit a wall. Why? There are 2 reasons to do that. Either your domain sizes have become so small that your time is actually more needed by the intercommunication between the cores rather than the solution. So suppose you have divided you started off with a region. By dividing it, you just randomly 2 by 2 by 2. You've over distributed the cores. Again, so this is also something to be careful. When you are running a system, you have been suppose given access to the Provega system here. It has some 20,000 cores. You take your 200 your course, run on 20,000 cores. You can run it. You can waste time, but you're actually wasting electricity. It is not expected to perform like that. So you should be testing out the performance of your code. To do that, and this is the core of your problem. The code performs well. Whether your problem, your grid structure is sort of enough to meet such high scales is something that you should verify and then do. Otherwise, what will happen is you have been given the time, you are wasting the total amount of CPU hours itself. Right? So this is what is called strong scaling. You take a fixed problem, you keep on increasing the number of cores, your time to reach the solution goes down. So the way we define speed up is T for 1 core divided by the T for n cores, T by Tn. So you can understand this will keep on going up. So there are several online resources. For example, you can look at this one. This is a blog from the KTH, Schizophrenic Aesthetic. I just did a standard search, and this is what looks interesting. So for the strong scaling, for example, you can find the speed up to theoretically something like this. But S is the part of the code that run on the single. That cannot be parallelized. It's a single part of a single core part of it. P is the fraction of the code that can be parallelized. The parallelized node section should be divided to the total number of cores that you're putting in. So you get a relation like this. Ideally, you should do something like this. When they have done the tests that they show, it fits like this. In the proposal that I was shown, this is what we were also showing, you can see. So ideal is something like this. This is still within the range, that's you are not getting the parabolic curve. Ideal is this. We have here. This is 10.5 cores. So this was done when Pluto was tested in our last year system. I think 2 orders. But I'm not sure which one. So this is called strong scaling. This is
I did not quite understand the scaling.
I have not talked about this scaling. So as you can see, this is the speed up that is happening, and given a table like this. Another way to demonstrate this is the total time to the solution. Just plot that as a function of force. This would actually linearly go down. In an ideal world, it goes down. It is plotted as number of nodes, but each node has, I think, 48. You can see that performance starts to deviate from here onwards, but it is not too bad. No one will expect your code to absolutely scale to hundreds, but it is possible. For example, Prayush, who mentioned yesterday, his code, there are new ways of deciding when to distribute what to what computers. But as long as you can show a scaling like this is important. So this scaling test is very important. Yeah, so this is the strong scaling, but it also depends on what is the S and the P that I mentioned. That's right. It will be flattened, but you may not see the flattening, depending on what part. If the large fraction of the code is parallelizable, it's just everything. Yeah. So this is a total time divided by the numbers. This is not the speed up that I was talking. Sorry.
And it's also log scale.
So other thing is weak scaling. Weak scaling, although it's supposed to be, this is something that is actually more relevant for demonstration. What you do is, as I said, if you have a fixed grid of the problem, you keep on investing cores in it, you inevitably run into a situation where you are, interconnect dominated. In a weak scaling, you keep a problem, but as you increase the number of cores, you also increase the size of it. So that the average computation per core remains almost constant. So that is a load balancing. So that you keep the load on each processor same. This is a better way to demonstrate the performance of a code that you would run, for example, on 2,000 cores machine somewhere on 3,000. Those are very typical numbers. Way we do production runs, we run them on 3,000 cores, even large. So weak scaling is important. For example, in this KTH slide, look at the weak scaling numbers. So this is the total time taken, and it's constant. So even as you increase the total number of processors, total time should be constant because and it shows that your performance is not MPI connect, it is imbalance. So these are the two kinds of scaling, and weak scaling plots are this. Weak scaling actually will go something like this. 1 second. This is the X is the single core part of the code plus P times N. If P is the parallelizable, you just invest more resources, you can parallelize. So that goes as a straight line. So scaling, that's why, is very important to demonstrate. And this is a language separate system administrators understand. And that is a language they use to evaluate your application. Now, once you do it once in your lifetime in one computer, you are done. Before you go to a new system, it's always advisable that test the scaling of your code. More importantly, what is also that you should mention is what is the memory requirement? You should test it out. You should profile your code to see what is the amount of memory being allocated in front. And then because you have to justify that if you have 2 GB per core, will that be sufficient or not? In most of the applications, I think also this one. You have to, for example, I have to mention what is the minimum amount I require to achieve the science and what is the maximum. They give something in between. But this is a total memory that I'm using. So total memory is the memory per core multiplied by number of cores. But you have to be careful that, for example, in OpenMPI distributed memories or shared memory systems, you may not need so many cores, but you may need large memory. So for simple fluid problems, you may not run into this problem. It will be just a linear division. But for more complex cases, you have to be aware of memory requirements. Yeah, so this is another thing that I wanted to share. This is from an Australian proposal for, I think, 6 million or so. Present your 6.5 that we had requested. Present your runs that you would get if you are able to upload a PDF system or present a proposal in a clear table like this. This always helps. If you have a different list of parameters, this is all good practice of writing a proposal. List it out like this and the effective computational cost. So KSU is similar CPU hours, let's say, it's just a unit of calculation on the NCI side. And if you demonstrate in this way, it becomes very clear to the committee if they have to give you less time, where they will come. So, and of course, these facilities are oversubscribed. If you demonstrate, no, I absolutely have to do part A and part B. If part C is possible, that is good. They will give you part A and part B. But this will only be possible if you have a well-structured proposal. Yeah, so that's the last things I wanted to mention was job submission script. So this is a typical job submission script. I think this was not even covered to you when you come to the. So you see the kind of inputs you give total number of CPUs required. So this is a submission script for the Australian facilitator. You have to get the total memory required. So this n CPUs is 48. Now, in several systems, you have to also give the number of nodes required. In an ideal system, you would find that the total number of CPUs is just a node times the number of cores per CPU. However, if you're running a job that, for example, just some small analysis scripts, you will just have the 2 nodes or 2 cores or something like that. So the total number of cores will be less than the number of cores. But in such a case, I think it's always advisable if there is a possibility to also mention the number of nodes. What it does is, otherwise, it will just distribute your job to different cores wherever it's needed. Otherwise, it blocks a node and then puts your job. Okay. It's always good to define it in this way. Then there's something called a queue. So, for example, my queue is called a normal queue. In most supercomputing facilities, you have 3 different levels of queues. One is called a normal queue, one is called a low priority queue, and one is a high priority. Names are different. High priority queue, for example, in the student system is charged 3 times the normal queue. For the normal queue, for example, every minute you give is deducted from your allocation in terms of total amount of CPU hours. If I use the executive queue or the high priority queue, 3 times. But the high priority queue also has limits. Why is it required? For example, if you change a small thing, you want to see if it actually works or not. So you run it for 2 hours and then check. There is a meaning behind using a high priority queue. Do not abuse the high priority. In several facilities, for example, such kind of limits or prompts may not have been given to you, but you yourself should be, full that you use the user systems properly. Then you get the total wall time, and that's it. You just submit this batch. Okay, yeah, then you have to load the module that you want to run. For example, they are loading Python 3, but you MPI, example, and then just give MPI run process. Okay. So this is a typical job submission script. This becomes only relevant later on if you actually submitting something. And the last, okay, so maybe I just wanted to flash the specifications of typical clusters using. For example, these are the systems. You can see it now? Yeah. So this is the Gali system in the Sri Lanka computing facility. It has 2.5 lakh cores. Okay, with a total, I think the FLOPS or something like 10 petaflop or something. There are 3,000. So there are different kinds. The reason why I'm showing you this is you can see there are different kinds of nodes available with different kinds of architecture. Some nodes have higher memory per node. They are more advanced. But they are also difficult to get access to. So when you're running an application, whether Pluto or something else, in probably general terms, you should be aware of what is the memory requirement of the job that you're doing. So all of this planning that you have before you even apply. Okay, I think that is it. That is more or less the yarn that I wanted to give with my experience. Prateek, Bhargav, you want to say, add anything to it?
I think Dipanjan has covered most of it. Now that he has listed here, one of the important aspects in computing, writing a computing proposal is how much time. And so that's very important. So the best practice would be that you have a small cluster at your own place. You work out, you try to see how much it is, and then use theoretical scaling to basically compute it. So we use, I'm using a compute cluster in Germany, and I was just checking at the usage that I know for advance. It is about 50,000 CPU hours. Okay, so it is 50 kilo CPU hours every month. Okay, so now that's almost on an average. An average thing over the year is about CPU hours. So I think that is what is really required if you want to do hardcore simulations. And Dipanjan mentioned about the queuing system. That is very, very important. And I mean, if you want to use supercomputer, you have to be very responsible. You can just not physically use it as your laptop or your desktop. Be very responsible in using it. But there's another important aspect because we are all kind of it is very bad when we are doing this. We cannot local install. clusters. All the good clusters basically follow this environment modules, which are essentially there. So there is this idea about module share. So essentially, if you want any module like Python or Visit or anything, it will not by default be there in your library. You have to basically call it. It will be there installed, but your environment has to be active. Okay. So don't install your own package in your own machine. That's not allowed. Not allowed. Okay. So you have to be very, very careful, responsible in using the clusters if the cluster access is given. I mean, there is these. I mean, of course, at your stage, perhaps you will not be able to apply anywhere. But you can collaborate, or if you go outside, for example, you are going to the Max Planck, go outside, you basically try to use these clusters, you will use very, very carefully. You cannot basically just keep on running these things. And just don't basically run your simulations with largest number of nodes.
Just one more point. Please do not run your code on the head node.
Never.
Whether it's an institutional cluster or the other cluster, you'll be kicked out. Really, this is the problem.
So yeah, you definitely never. I mean, logging node is logging node. There is another important aspect. Usually, the storage. Okay, because most of your simulation has a lot of data. Now, what happens in these computing clusters is either you can ask for some storage already, so that they will be there, like always be there. $30. But usually good clusters, if you store it in some Splash data file, after every month they will remove it. They will not even ask you. Okay, so if you don't take data, your data is gone. So big simulation kiya, 1 mahine ka sab gaya. Everything will be gone. Okay, so it is very important that you also take care of your storage. Okay, so most of these computing computing proposals also require you to request how much storage space is required, approximate storage space. Okay, so apart from your CPU time, your storage space is also very important. Okay, and don't install anything on the head node, neither on.
Yeah, also on the storage, there's something I call you pointing it out. I listed out. So while you are proposing it and designing a simulation, it's absolutely critical for you to map out the storage, and you have to be judicious about it. For example, I'll give you again the Indian environment that we live in. In IUCAA, we have a 1 petabyte disk. 1 petabyte is unthinkable for us when you use international clusters. Here, I get reports from us that 90% is used, please remove, and nobody is removing it. Why? Because people treat them like their own desktop. We do not have a crash policy. So in this kind of small scale system, you are more lax and you are pampered. But it happened to me. So I have run something, gone somewhere for Christmas, came back and saw my data has gone. I have again spend my CPU hours to rerun those models. Happens. But also more importantly, when you are running large scale production runs, you have large scale grid sizes. You cannot just dump a lot of data just for the sake of making movies. That is when we need a lot of data. Or if you want to analyze something at a much shorter frequency, use specialized scripts within in situ of the code. For example, Pluto has some analysis script. All the other codes will also have something similar. If you want to make something just for the plots, make slices. Modify your output structure. Again, that's why you need to go deep into the code and modify things. Modify your output structure so that it produces slices at one time. Because space is very important as well. And the thing is, they will remove it after 1 month. So you have 1 month's time to 1 month or 3 months, whatever it is, to get the data somewhere. What will you do? Where will you get the data? Will an institution provide a 100 terabyte disk to you? No. 10 terabytes is also quite difficult, and it's on those portable disks which can break in the Indian somewhere.
So basically now modern supercomputers or these clusters have clouds. Okay, so you can actually also get access to those clouds. And so that cloud material will stay with you.
So there are storage like mass storage where you have on tapes you store the data. But the thing is, those kind of data is difficult to access for analysis. You have to load the data again on your spreadsheet, analysis, and then push it back to the storage. So you have to be a bit careful with this.
And then sometimes clusters also have visualizations. So essentially, you don't need your data can be there in your cluster itself, and you can do your own visualization there. for example, running transactions or to visit over there, that's absolutely possible. So the idea is you don't have to bring your data. Then you have to also be careful that if you don't bring your data, don't send it to their data will be gone. So you have to be very, very careful. Okay, so all these things are very important. So writing a computing proposal is just not just writing a standard. And the scientific aspect should be highlighted. This stuff. But you should have peripheral knowledge of what you essentially want. And that is, remember, the experts are kind of evaluating that. So they would know exactly how much you are taking and how much it's actually the truth. Okay. So be very careful about this. Make all the future. Even when you are using your normal products, try to see what is doing. Just use the core like chat. We never go and see the concept word. He has written down Intel Skylake. What is Intel Skylake? You should look into that. So that is what our thing is. It's not just snacks. Then simulation, yeah. And occasionally, maybe they can have salsa. This Intel Xeon scalable. What is scalable processors? What are these processors? What are the technology that? That also you should be aware, because if you are aware of that technology, it will be easier for you to write it. Okay. So it is very important. You should be aware of the peripheral knowledge also. Just not doing alone science. Okay. So I think.
Wrap up, any questions?
Any questions? Anything that you want?
General discussion. So any questions?
What is the head node?
What is a head node? The login, very first login. So the EU structure is the login has a high memory node and also support multiple entries. But from there you submit. I showed you a script with where I mentioned the number of cores, number of memories. That's called the bash PBS script or something. You submit the script and then login node then has a schedule that distributes the job in wherever it's possible, depending on the queue of the system. So login is only for submitting, compiling and submitting.
It is not for
Never.
Never.
What happens is if you run, login usually has number of cores and high memory. If you run your system on it, it becomes very slow. People cannot access core.
They don't even log in.
Exactly.
And then it is not very high number of cores also. It will be like modest cores, 30 to 64 core machine will be there. It will be not very high.
But this is a basic problem every new user of the HPC system makes. That because they're not aware of how things go. So before you go into a HPC and run things, please consult the user guide thoroughly and talk to experts that have already used. Okay, to understand how to go about it.
Exactly. And also now there will be hybrid CPU, GPU. So you also have to be very, very careful about how much GPU you ask, how much CPU you ask, and so on. All these aspects should be there. Any other questions?
Some creators they take this and give you more hours.
No,
There is a problem at
no. That will not happen. They have multiple team systems. So they will always have a kind of a backup of your data, right? All of that. So for example, if there is hard disk failure, so usually these big supercomputers, they always work on something called as a RAID mode. Okay, so they will always have a backup of any. That will not happen from that. I haven't experienced that any time.
No, but for example, if you're talking about downtimes of the first time,
They will have maintenance.
but they will not recommend it. And that's also happens for observational astronomy. You have you get 7 nights on a telescope, you get a dark sky or
that is like
No, but
that's part of
but I mean maintenance. Usually periodic maintenance are done. They inform you before only. Then don't run.
So flags for GPU also have to sometimes mentioned explicitly.
flags for GPU, yes. Sir. Any other those are raised hand back?
It's a kind of server side of some options. Is that what?
No. This is basically for certain visualization process of interactive. Node meaning you can basically have like a virtual machine in front of you. You can just basically open. It's just a Linux terminal open for you, and you basically can just.
Interactive mode means you can do an SSH.
So you can do all sorts of
SSH GUI and then so you can reserve that node, login node, that compute node, not login node. And then use that compute node for your analysis for a certain duration.
the smooth part is that it will always connect to your data, so you can just directly get it.
there is a small scale clusters which can be very common.
Usually small scale, what is small scale? You run it on the cloud. Cloud, yeah. Now that's available for everyone.
Such high processing. Not directly.
So, unless you have some access to some institutional facilities where they learn.
But you can use AWS to some extent, I mean basic ones, but
They're not
so
that-
they're not used.
they're not that-
Not to do such big signals. Not on this little thing.
Okay, should we end now?
Then,
Okay.
okay,
Right. I think